Okay, Ruofan,
okay.
I'm start recording. Please start your presentation.
Okay. Good afternoon. Today I'll present a paper published in ICML 2018. And this paper was selected as one of the best papers that year. The title is Obfuscated Gradients Give a False Sense of Security, Circumventing Defenses to Adversarial Examples. And the authors are from MIT, Google Brain, and Berkeley. The second and third authors are big names in this field. One of the strongest adversarial attack method called C&W attack was invented by these two people.
The last two people.
Yeah.
Yeah, so it's just named by the last name of
Kalinin and W. Yeah.
The Kalinin and Wagner. Okay.
So this paper is still focusing on adversarial attack and defense. As we all know, adversarial attack adds a small perturbation onto the image that can alter the predicted label. But the key challenge in adversarial attack is how do we find the correct direction of perturbation? Because a random direction rarely works. For example, in two-dimensional space, if my clean image is X and I have a decision boundary, I want to perturb X until it crosses the decision boundary. Then I have to project X towards those green directions instead of red directions. Right.
And there's some
So a random attack in two-dimensional space only have half chance to succeed. To find the correct direction of the perturbation, many adversarial attacks are gradient-based because gradient reflects how the classification score changes. That is where the classification boundary lies. Like in FGSM, it finds the steepest direction that increases the loss from ground truth label, and then we move X towards that direction. So now, as you may observe, the problem for gradient-based attack is that gradient-based attacks only work when the gradient can be computed and also the gradient is accurate. Given this intuition, some adversarial defense achieve robustness by masking the true gradient, such that the gradient either becomes non-existent or inaccurate. The paper uses the term obfuscated gradients to categorize those defenses. There are three types of obfuscated gradient defenses. The first type is when we have a function that is non-differentiable inside neural network when doing backward pass. Because the function is non-differentiable, then the gradient cannot be backpropagated. For example, if we replace the ReLU activation with a stepwise function, because stepwise function is not smooth and thus non-differentiable.
By the way, so sorry for interrupting. It's because the step rule is it is us. It is us who propose. So from my point of view, we report these step rules when we have lots of missions. So have you ever find some similar, or have you found some exact papers, or have some papers who exactly invent the same technique? As far as I know, there's some jump rule, like Google searches, jump rule. So the idea is something like the jump rule, so it will have to result like this. Something like this. So it's more like a jump rule. So there is a jump there. So somehow, but once compared to the jump rule, our step rule can seems to have a better property to preserve the original accuracy. And for jumper rule, there's an undefined undefined place here, right?
But why?
Oh, of course, it's somehow to see how far we jump, right?
Oh.
So jumper rule to make sure. Still something. Maybe it looks very similar. What do you think?
Yeah, it's very similar.
We call step rule and there's jumper rule. Yeah. So please go on. I think the step rule itself may not necessarily contribute.
Yeah.
May not necessarily may not sufficient to be a single contribution.
Yeah.
But we can go several steps further to see whether we can have a better defense technique, or whether we can have a more advanced attack technique. Okay.
Oh, okay. So this is the first type. They call it shattered gradients. This is when gradient does not exist or cannot be computed easily. The second type is called stochastic gradient. This is because we have a random layer or random transformation on input during test time. So that makes the gradient to be random. For example, if I randomly drop out some neurons during test time, then a single estimation of gradient does not reflect the true gradient.
Yeah, please go on. It's quite easy to understand. So maybe I suggest you raise some questions to the audience. So I think in the past presentations, I'm the one who always raising the questions, and you are the only one who defends it. But I think it is better way to using the Socrates, to make the description in a Socrates style. That is, we have multiple people to be the attackers, and we have multiple people to be the defenders. So we can gain the knowledge through attack and defense, so that we can spot the ideas in more efficiently. So Ruofan, here my question is that can you raise the question to the audience to make sure whether the audience can fully grasp what you talk? So maybe, but you understand my question, right?
I understand, but I don't know what
to ask. So here is so maybe let me raise a question first. In your last bullet, you mentioned the simple estimation of the gradients does not reflect the true gradients. Maybe you can ask someone to raise the examples. For example, maybe you can ask Xiaolin, Yihao, Xuezhi, etc., or Jingguo, etc., to let them to raise the examples why the single estimation gradient will not reflect the true gradient, and how the dropout can really affect the gradient estimation.
But this is an example.
Yeah, you can see some of the weights has been dropped, right?
Yeah. And because those neurons are dropped, so when you compute the gradient computed on the left-hand side graph is different from the gradient computed when you use the full network. So this gradient is not the true gradient. It's just an estimation of gradient. Yeah.
And after dropouts, the gradient can either get larger or get smaller, right? Here, they have multiple possibilities. Maybe one of the questions I will ask is that if in this case I'm the attacker, so what's the prompt or what's the benefits, what the pros and the cons of this attack, of this defense technique. So usually when we, for example, one typical defense technique is adversary training. We need to keep retraining the model. You always bring the pros and the cons. For example, we have a better defense. We have a better way to. We now have a way to defend the adversary attack. But what is cost?
Oh, you're asking me, or
I'm asking the audience.
Oh.
So, so is there anyone listening? So maybe I'm asking. So maybe the first question goes to Xiaoling. Is Xiaoling there? Hello, Xiaoling. So, what do you think it is? What do you think? What is the cost of this defense technique?
The cost.
Yeah, the cost. For now, let me repeat the question here. So this is the original neural network models, and these models defense attack because it can by dropping upon some neurons. So if we drop some neurons, the gradient, for example, the gradient here. So anyway, the gradient actually we were talking about whether we need to so the original adversarial attack will indicate that we need to change the pixel here, right? Suppose giving that this is input layer, and if we drop it here, if we drop these neurons, and the gradients of the gradient information disappear, so it will have a different results. Maybe it is not so reliable here. But what is cost by dropping off these neurons?
You mean cost, C-O-S-T, or
Cost. What is cost to drop out the neurons to defend the adversary samples?
I think the cost is pretty low, right? You just need to drop them.
So have you ever learned what is dropout?
Yeah, you just randomly throw out the weight of the neurons, right?
During training or during testing?
Training.
And this time it drop out
At
the testing. According to the standard dropout training, according to the standard dropout strategy, we only drop out the neurons during the training. And for what? Do you know for what?
For to avoid overfitting.
Yes, but why we do not drop out during testing?
Because you need to reflect the true situation of training.
Ruofan, do you know why we do not drop out during the testing?
Because we want to retain the testing accuracy. Like if we drop out neurons, it's like we drop out the features. Yeah.
My answer might be a little bit different, but I'm not quite sure. So I feel that if we drop out the neurons during the testing, it is possible that if you now drop out introduce non-determinism, or it will reduce non-deterministic prediction, right? So if we do the dropout during testing, it means that the same images, for the same images, the model will have different predictions for each time, right? So that is necessary what we would like to avoid. So in this case, so let's come back to the question here. And I think from my point of view, Ruofan can correct me if you think it's not correct. The cost is that now if we have a model which allows to apply dropout for the predictions, it is possible that for each image, we will have non-deterministic prediction results. for given image, it is the people, and one time one time it will predict as this Mike, or one time they will return it is Jack, or next time they will report someone else. So that is a deterministic result. So
Yeah.
usually the non-deterministic result is what we want to avoid. So from my point, that is one of the cost or pros that it has. So does the paper mention how does the model address the non-determinism?
No, but I once read a paper. So the paper said even if we apply dropout during test time, if the model is trained to be very robust, then for the clean images, the prediction shouldn't change much.
So
Because
so they require the model to be very robust.
Yeah. Because dropout
but if the model is very robust, then the perturbations on the layers, it almost make no difference. The perturbations on the okay, there may be a trait. There may be a trait. So the point that if the random perturbation on the images will not change the results, right? The only adversarial perturbations will make the result change.
Random perturbation.
So given the images, if we apply random perturbation on images, if the model is well trained, the results usually will not change.
What?
So I'm not sure whether I expressed myself clearly.
Random perturbation is this. So this is adversarial image or
this is original image.
Original image.
Yeah, if we're given the original images, if the model is well trained, and we apply random perturbation on the images, then the prediction will not change much.
The prediction will not change much when the image is looking at like the training data. So because here,
of course, I'm talking about the training data.
Yeah, but here you apply random perturbation, so it's not like training data. Then I think the prediction will also change a lot. Yeah.
Well, remember when you report a paper saying that random perturbations have very low probability to fool the model. Because when John is here, he wants to do some experiment. He wants to do some experiment. He applied random perturbations on both the input side of this model and the input of the object detection model. For example, apply random perturbations on the screenshot or the local images, and he finds that the model is actually quite robust. Again, these kind of random perturbations. However, if we apply adversarial perturbation on the images, the model is influenced a lot. And also, I remember that you once have a theoretical proof in one of the reports saying that random perturbations have really a very low probabilities to go to the direction change, because in the images is a kind of a high dimensional input. So the random perturbation actually does not work. So when we come back to here, so if we apply random perturbations on certain layers, somehow it means that it will keep the prediction. The random perturbation is not so much. So the prediction will somehow still preserve, right? So the cost is just it might be a theoretical cost. Might be. What do you think? But the point is that let me clear that. So here there's two points to make. First, if the random perturbation or the dropout is due, we can consider dropout as the random perturbations on one layer or several layers, right? So if the perturbations on layers can implies can still have robust prediction. So it means it is still have somehow deterministic predictions. So does it imply that the attacker can still the adversary attack can be largely successful, because if the result is deterministic, then the gradient will somehow preserved. So it means that somehow it will have preserved the gradient. Somehow preserve the gradient. So that also means that when the gradients are preserved, so it means that the adversary attack can still be successful. Is that correct? So we can see, suppose here are the layers. So suppose we apply random, now the dropout means that we apply random perturbations on the layers.
Yeah.
And the random perturbation on layer or dropout actually can, what you mentioned is that it can actually still provide deterministic predictions. So it means that this network is quite stable and robust against this perturbation. And that means that the original gradients can still somehow preserve.
I don't know whether this error is correct.
This implication may not be correct.
May not be correct.
Consider here. Suppose consider here. Suppose there's a gradient. Suppose this is a y, right? And this gradient is partial y over partial x1, right? And actually is calculated by a lot of the weights in the network. And even if we drop out some neurons here, right? So they may have limited contributions to these gradients.
But this part is related to forward pass, so it only relates to the weight itself and also the activation value. But this gradient part is related to the backward pass, so it's partial derivative. So I don't think there's an obvious relationship between forward pass and backward pass.
Sorry, I may miss your point. So when we perform or conduct forward propagation, do we still drop out the neuron?
Yeah. But I mean, here is forward pass, right? It is not related to any gradient here, but here you draw a conclusion that the gradient is preserved. I think may not be true.
The point is that if we drop the neuron here, definitely it will influence the result of prediction, right? For example, it will, so the original prediction was 0.9, and after we perturbate it a bit, it will drop to 0.7, right? But it's, given that there is a confidence drop, but 0.7 is still above 0.5, so the output will still be preserved. So my point is that yes, the gradients will be influenced by dropping. So anyway, once we drop out the neurons or perturbation on the layers, and the final output is influenced. However, if it is not influenced much, does it imply that the gradients will still be influenced, but not that much?
I think no.
Why?
Because like what I said, so this part is only related to the weight itself and the activation value, but
I think the only thing we can think about is that if we drop down neuron here, and the neuron.
No, the gradient will not be preserved because during test time your gradient does not change. So So this is the original gradient after training. And yeah, you get what I mean.
Like, I get what you mean, but I don't
Yeah.
get your conclusion. No.
So my conclusion is that the gradient is not preserved after training. So for example, after training, the gradient for this neuron is from these 4 directions, right?
Mm.
But now after dropout, your gradient only come from these 2 directions. So the gradient has decreased, right?
But your forward propagation is still decreased. So
No. I will scale up after dropout. So for example, if I only left with 2 neurons, then I will time some scale factor to them to make sure that my confidence does not drop much.
So the point is that we can still scale up after for the back propagation.
For the forward propagation.
I understand you do the scale. You do scale up for the forward propagation,
but not for the backward. But
I
not
mean,
for the gradient.
But now I'm the attacker.
Yeah.
So if you can do the scale up for the forward propagations, why can't I do the scale up when
you can scale up the gradient, but if you add up these 2, then times 2, it is not equal to the original sum of 4
the same logic applies for the forward propagation.
Yeah.
So my point is that if forward propagation, if dropout will not influence the forward propagation, and it may not influence the backward propagation as well.
No, it should influence the backward propagation.
Definitely it will influence.
No, but there's no scale up. There's no scale up.
What if we apply scale up? But you know the result is this 0.7 is the result of scale up, right?
I think shouldn't drop so much, maybe 0.8.
Okay, 0.8.
Yeah.
But so when we do the propagation of 0.8, so the scale up effect has been the scale up effect has been preserved as well.
No. The gradient is not scaled up. Just compute the gradient in normal way.
But the starting point has been scaled up.
No, during test time, as I'm the attacker, I don't know which neuron is dropped out, so I cannot apply scale up. You know, I don't know which neuron to drop out, so I don't know what scale up factor I should multiply.
It doesn't matter because when we start.
No. You don't know how many connections has lost for this neuron. So you don't know whether multiply. It's an assumption. Like during white box attack setting, the attacker has no knowledge in test time randomness. So you cannot.
It's ridiculous.
Why is ridiculous?
When we have the models, we have all the knowledges. Why can't the attackers don't know the dropouts?
But if you know everything, then attacking is just a trivial task. Then there's no space for the defender to play. So usually we will not assume the attacker knows everything.
When we do the adversary, the normal adversary attackers already know everything. It knows every way here.
I think is
so okay, I think we should call it end for these discussions.
Yeah.
But somehow we need to leave these as open questions. Maybe we can investigate it later. So here is one of my points. I'm not sure whether it is correct, and the Ruofan have a different point over that. But here is I just make it a more clear point. So suppose the random perturbations. Suppose there are random perturbations on the images, suppose the model is robust. The random perturbations on the images will actually not reflect the prediction result as well. So even if there is a perturbation for non-deterministic results or non-deterministic input, but always have a deterministic output. right? So this is where we start. So let's move the perturbations or non-determinisms in the intermediate layers. And if we somehow change the intermediate layers, but we can still preserve the determinisms of the final output. So here we can infer that the non-determinisms or the random perturbations on the input layers has minimum effect on the output. So this somehow means that these dropout neurons can change the propagation process, but not change that much. That may also imply that the gradients here may not be inferred. If we do the back propagations, the gradients here may not infer that much. In this case, the attackers seems to able to also take the existing gradients to the attack. It might also be successful. Of course, that is paper. The reviewer or the researchers must show that this defense technique, the researchers might show the technique of this approach. But somehow, I still have feel that if the dropout does not influence the deterministic results of the output, it somehow may not influence the gradients so much. Okay, maybe we can call end for these discussions. Keep going on.
The last type is exploding and vanishing gradients. So this happens when the defense consists of multiple optimization loops or multiple network that makes the whole network evaluation very deep. So any direct backpropagation gets exploding or vanishing gradients. For example, here we have a defense network called defense scan. This defense scan has in total 3 networks. The first network is an optimization network and a generator network and a classification network. So if we do the backpropagation in normal way, the backpropagation path is really long. That makes the gradient either explode or vanish. This question is very simple. So just as a recap, in total, there are 3 types of obfuscated gradient defense. The first one is non-differentiable layer. Second one is random layer or random transformation. Third one is exploding and vanishing gradients. So I was intending to ask this question, but I find this question is really simple. So for a classifier that takes 331 times 331 input, the defense first randomly rescales the image to R by R image, where R is randomly drawn from the range 299 to 331, and then randomly zero pass the image so that the image becomes of this shape. Then we feed the output into the classifier. So this defense definitely falls into the second type, stochastic gradient, because we have a random transformation.
So you just answered the question yourself.
Yeah.
Okay.
And then the paper summarized some phenomena we may observe if obfuscated gradient defense is applied. First, in general, iterative attack should be strictly working better than single-step attack. But when we observe iterative attack is worse, then we can infer that the gradient we compute is inaccurate. Secondly, when black box attacks are better than white box, or random attack are better than white box, then we know that something wrong with the gradient computation. In addition, when unbounded perturbation does not reach 100% success, or increasing perturbation strength does not help, then we know the model might be using obfuscated gradient defense.
Let me think about it. Let me think about it here. So here are the black box attacks. So what's the difference between 2 and 3, the black box attack and the random attacks?
Random attack is the example I illustrated in the beginning, is that I just take a random direction. Black box attack is I know the model architecture, I just don't know the model weights. So I train a local model for myself. Then I use the weights I have trained. Then during attack, the gradient is computed from my local model.
So
yeah.
So yeah, that possible the plateau is a little bit different. For example, in the white box, when it was performed the adversarial attack, I think that's more like a heuristics, right? So
Yeah.
it's more like heuristics if you have such certain observations. For the white box attack, we may still have the local optima issue. So that's when we apply the adversarial attack. We move the sample to a local optimal, and we can never get out, escape the optimal. Then it's stuck. But if we retrain the models, the plateau is a little bit different. There's still possible that the black box attack is better than white box attack, but there's no obfuscated gradients here.
Yeah.
But of course, so it is more like necessary but insufficient conditions to do the inference.
Yeah. It's like when you observe these abnormal things happen, then you can guess that maybe there is a defense.
So here the attackers will still so this is more like the observations or the behavioral observations when we look into such phenomena, and we can infer the obfuscated gradients. So think about whether we can apply some static analysis for obfuscated gradients. So maybe we can look at the 0.5, 0.4, and 0.5. When unbounded perturbation. So what do you mean by unbounded perturbation strength?
Perturbation strength is like the step size you take. For example, like in this graph, if I'm sure that my direction is one of the green direction, and if I take a longer enough step size, then definitely I will reach the decision boundary in the end.
But it may not guarantee we can still preserve the semantics.
Yeah.
The point that, of course, when we take such a long steps, we can cross the boundary. Yeah. But if we cross the boundary, that does not mean the semantics can be preserved.
Yeah. So when we take unbounded step size, then maybe the image will look very weird. But
yeah. So why do you take a space? Why do you take a line space between 3 and 4?
Yeah. Oh, this. Because I feel these three can be grouped together, and these two are somehow related.
Yeah, the first three are talking about the attack, so at least the last two are talking about the perturbation strengths.
Yeah.
So that's more like a hypothesis, But I'm thinking about whether it is possible to infer from the model structure itself. So I disagree with you on one point that attacker does not know everything. So given that we have talking about a white box, so we can play with the models as much as we can. We can apply what ReLU function. We can know what ReLU function is used and how they design the ReLU function. How do they design the sigmoid functions and all the structures and architectures and all, and all the weights and all. So in this case, we can apply static analysis over the whole network to infer whether there's an obfuscated gradient dependence there. I get my point.
But if you know everything, then you definitely know there's a
No,
defense.
no. I think we have discussed this one before. So the point is that the real models may apply it on the cloud. So suppose it's a cloud. You understand what the cloud is? It is actually a web service. The model actually do the job here, right? The model do the job here. So you give it an input. The input could be a people, an image of people, can be a void, a subject, and it will give an output, right? So this input output. But the attackers, so they have different assumptions of the attack. The first is a black box attack, and second is a white box. Since we're talking the white box, this models has been leaked. The point that we have exactly model in prime here on our local machines, and we know everything about it, and we also know there's a model on the cloud. So the trick is that we can only change the input here, but we know all the details in the model in prime. So based on the reference of model prime, we can construct input prime I prime and feed into the cloud. And the cloud and this information is giving this I prime, the cloud or the model on the cloud will give us the output as we expected.
Why do you just use the output from M prime?
We cannot use the output from M prime because
you have everything here.
Maybe the output. This is a service. This is service on the cloud. So
yes.
So the output generated by the local M prime is not kind of not certified. And if this is the output generated by the service or by the cloud, this is somehow verified. And this O prime may be used in the other system as well.
Do you know the model weights?
Yes, I know. If we would like to apply the adversarial text, we know everything of the model.
Then it's white box. Then what is difference between the model on the cloud and M prime?
So we take the reference of N and perform the adversary, so that we can compromise. We make the service return the wrong result.
Yes.
The point. Maybe make a difference. Maybe I'm raise the example here. So suppose how to raise the example here. So suppose the model is deployed on a cloud. Maybe this cloud is from the government, right? Or from the US government, the Chinese government. And suppose the result is generated by the government server. So this result may have certificate, and it will be believed by more people. And if I have an exact model here, of course I can change everything here. If this model is on my machines, I can even change the weights of the model, right? But it doesn't mean anything. So this model is just a reference for me to infer how can I change the input so that the model on the government machines will return the wrong output.
Okay.
Yeah.
Then can I ask you one question? Does it mean that the O generated by M prime will defeat the model on the cloud? So if we can defeat M prime, does it mean we can defeat the model on the cloud?
Yes.
Okay.
Okay, I'm thinking about, so let's back to our discussion point. So we know every detail of the models. We know what review functions apply, what activation functions apply, but we need to, but the only thing we can change is the input. The only thing we can change is the input. And let's back to my point here. So from these slides, the authors proposed 5 points for us to infer whether the obfuscated gradient defense. And why not we just infer or apply the static analysis for the model and prime? And then we know everything there, right?
Yes. So they just list some phenomena. Yeah, it's just some rules, some heuristics.
But these obfuscated gradients here are all white box attack, right?
Yeah.
So if they were
No, this is not their main part. This is just some summarization. Yeah.
I understand these are summarizations. Given that because they have the observation or have phenomena that the white box attack is better than the black box attack is better than the white box one. So that means we already have the white box one.
Yeah.
Right. So if we have a white box ones, why not we, for example, we write a checker to go through the model architectures, model details, then we already know the answer. So as long as we write the rules, for example, we find that there's a non-differentiable features in the model. For example, all the normal model will have a rule, but in this case we have a step rule here. So suppose we have a heuristic to detect this kind of the non-differentiable features for the models, then we can already infer that there's obfuscated technique. Even further, when we know which part is the gradient obfuscated or gradient masking technique, we can somehow just replace the technique, replace the gradients, making the model have the same performance while still vulnerable to the attack.
I think here they just want to list what will happen if we use the defense. It's not to detect whether there's a defense.
Suppose a model is leaked, I feel that there's a chance of using standard analysis for the model. So I'm talking about something else. But since we already have phenomena, so I'm just raising questions why we only leverage the phenomena to infer this obfuscated gradient defense. Why not we dive into the details?
Yes, I will introduce later. This is only the background section.
Okay, so okay.
Yeah.
So let's see how far we go. Because I'm thinking about the other research opportunity there.
So this paper is trying to prove that all the defenses I have discussed, like using obfuscated gradients, give a false sense of security. It then tries to circumvent these defenses. But the challenge is that since there are in total 3 types, and each needs to be addressed in different ways. First, here is their approach to attack 3 types of defenses. For shattered gradients, they are going to attack with backward path differentiable approximation. Suppose a network F has in total J layers, F1 to Fj. Then one of the layer, maybe Fi, is a non-differentiable layer. Then we just need to find a J function to approximate Fi. Then during backward pass, we replace Fi with J, and because this J is a differentiable function, so the gradient can flow.
So they have already, okay. So the BPDA is what they proposed, right?
As for stochastic gradient, they are going to attack with expectation over transformation. A stochastic gradient happens when the input layer, when the input is randomly transformed with some transformation function, or the network has some random layer. So instead of evaluating gradient once, we are going to evaluate gradient for the same examples for k times, then take the average. So as we all know, if we take the average, it is a more accurate estimate of the true gradient. Right.
Very easy to understand. Please go on.
For exploding and vanishing gradients, we attack through reparameterization. We have exploding or vanishing gradient because we may have multiple networks that make the model very deep. So assume F is the classifier and J is some optimization network. And this J is usually trying to purify the adversarial images, which is to remove the perturbation inside adversarial image. So it is this function J that makes the network very deep. Right. So the idea is that we want to avoid J in backpropagation. First, we make change of variable. As an attacker, we aim to find X adversarial. But now we don't find it directly. We find a hidden variable Z adversarial that is related to X adversarial with some differentiable function H. Then for the attack to be successful, we want Jx adversarial equal to X adversarial. So the idea is that J cannot purify X adversarial anymore. The images before purifying and after purifying are the same. Right?
I have no problem understanding that. Maybe you can raise a question to the other audience. We can finish the introductions and you can raise a question.
So which can also be expressed as this because we just plug in X adversarial with HZ adversarial. Then FJX adversarial, we can just replace X with Z. So we derive this. And you can observe that the J function actually disappears, right?
Yes.
So because J is the one who is making trouble, and now we get rid of J, we only left with F and H. So we no longer need backpropagation through J. Right.
Okay, I think it's very clear. You want any question here? Hello?
I don't know.
Maybe you can somehow explain it a little bit, or do you have any other full explanations with examples here? So I think here you are talking in a very abstract way. I'm afraid, except me, no one else is quite for. Is Qingzhou still there? Qingzhou and Yihao still here?
Yes.
Hello, yes.
Yeah, so do you understand this part? Well, somehow, do you have any background of the voluntary sample generation? Oh, Yihao.
I don't have much background on.
And how about Qingzhou?
Yeah, I don't have much.
Okay, so yeah, I'm not sure whether it's appropriate. Xiangling, is Xiangling here?
Yes, yes.
Yes, do you understand this point? You understand it, right?
Yes, because you need, because the network is too deep, therefore it might cause exploring or vanishing gradients. So you need to somehow not erase, but make it shorter, not that deep, so that you can compute a gradient. So here you just make sure you replace the deep G function with a differentiable edge, right?
Mm.
Yeah.
Yeah. Exactly. Yeah.
And can you further illustrate what is Z adversary means?
Me?
Yeah, maybe Xiaoning. So make sure. I think Xiaoning is good. It's quite good to abstract to grasp the abstract point. So, but there are some still technical problems here. So Xiaoning, can you explain a bit more? I'm trying to see how deep you understand this. So can you further illustrate what is Z adversary means? So, and what is the relation between A adversary, or X adversary, and Z adversary?
From my understanding, I think you need to define edge here first, and then Z would be edge inverse X, right?
And what is this Z can be used?
For example, I have a decoder function. So if I feed my X into the decoder, I get a vector Z. So this Z is a hidden vector that can represent my X. Then the H here is just the inverse of the decoder function.
You are talking. I think you're talking.
An
about,
example.
You
An
mean
example.
what do you mention? What do you intend to say the encoder function? You encode X into Z.
Encoder. An example would be encoder.
So so what do you mean H is a decoder function?
Actually, H can be any function, but just as an example.
I'm talking about examples. Yeah.
Yeah.
For example, is H is decoder functions.
I mean, Z is equal to some decoder function of X. So X is the image.
Decoder or encoder?
Encoder.
Okay, this is encoder function. Okay.
Encoder. And Z is the vector you get out from the encoder, right? So then here, my H would be the inverse of encoder.
Yes, so the decoder function, right?
Yeah. So you can understand it as Z is just a representation for X. Okay. Yeah.
I still feel that if we introduce the H here, it may not be necessary. So, so I think this Z is kind of specific for the autoencoder decoder, right? If it is not a or decoder, if it's not a encoder decoder approach, then this Z may not be where represented here, right? Suppose there's another technique. Yeah, so this not that makes sense. Okay, maybe you can illustrate it with more examples. I think there's some follow-up slides here.
So now I have finished my illustration for the approach part. We will go through the experiment. In the experiment, the author defines threat model in white box setting, where the attacker knows model architecture, model weights, defense technique, but not test time randomness. And the attack method used here is, first one is PJD. PJD is just iterative FGSM with a random first step perturbation. And also the method they invented before. So in total, there are 3 research questions to answer. The first question is it effective to attack shattered gradient with backward pass BPDA, backward pass differentiable approximation? So here they attack one of the state-of-the-art defense method called thermal encoding. This method just adds a non-differentiable input transformation before feeding into the classifier. The encoding function is as follows. It just transforms the real value pixel values into an encoding vector. And the encoding function is as follows. First, my input is the real value A. This A is between 0 and 1 because my pixel value are normalized. The output is a length 10 vector B. And the case entry of B can only take two values, either 0 or 1. It is 0 when A is larger than K divided by 10, and 1 otherwise.
Where is the K?
K is the case entry of B.
Oh, K is the case entry.
So, yeah. For example, if A is equal to 0.1, and we observe that A is larger than 0.1, but smaller than 0.2. So the encoding for A is just 0 followed by 9 ones.
So it's more like a discretization, right?
Yeah.
So it's changing continuous value into the discrete value. Give me a feeling it's more like this. So maybe I will digest it. Okay. So maybe you can ask someone to answer the question. What if B is equal to 0.58?
Okay. Qingzhou?
Yes.
Huh? Yeah.
Good. Yeah. Wait, sorry. So it's
So the question is here. If B, how does A can be encoded or when A is 0.58?
okay. Wait. Not too sure.
You can think about it.
What is? Oh, okay. K is the theta, right?
K is
okay.
entry.
Wait, I need to write it down. Wait a sec.
You can write on. You can annotate on the screenshot. And in the meantime, I suggest Xiaoning and Yihao, you can perform the same calculation.
So it's 5 zeros followed by 5 ones.
Yes.
Right. Yeah.
Yeah.
5 zeros. Thank you.
Thank you.
Yeah. Correct. Sorry.
And then maybe Xiaoning, you can present how you calculate it for Qingzhou and Yihao.
So what if A equals to 0.63?
Oh, you're raising question, right? You are not raising questions.
Oh, so what do you mean?
What I mean is that you perform the calculations for Qingzhou.
So you just erase the erase 8. Oh no, what I mean is you keep. Sorry, let me annotate. So you just keep this value, and this 5 means there are 5 zeros, and then you just add 10 minus 5 once. Because in this way it just means you have 10 possible values for B, and if your value falls in 0 to 0.1, or your value falls in 0.1 to 0.2, then this would be 10 zeros, and this would be 0 times 9 plus 1, and then you just, right?
The first thing is 10 1, 10 ones.
Oh, sorry, 10 ones. Oh, so yeah, 10 ones. So there are 10 possible values, and you just calculate what the real value falls into which factor.
So basically, you just divided the value into 10 ranges, right?
Right.
10 ranges. So basically, it's just to turn a continuous value. Hey, does it somehow relate similar to step-by loop?
Yes.
It's very
Yes,
similar to
very
step-by loop.
similar.
Right? Very similar to step-by loop here. So you have just like a step here. So Yihao, have you understand this one?
Yeah.
Okay, so basically it will just more like have 10, it actually have 10 grades here. So it is also possible that we have 100 ones. So in this case, and in this case, Xiangling, maybe I raise another question for you. Do you think what is the cost if we do such kind of encoding? What is cost?
I have one question here. So if you do this, then how do you train your model? Then your model would be non-differentiable.
I think is the back propagation will stop at the transformed vector. So when you are doing the training, you first transform all the original image into the encoding vector. Into the encoding image, and when you train it, you just treat this as your input image. So you don't do back propagation from your transform input to the original input. Yeah. But during test time, you add this transformation function, so the attacker cannot flow their gradients.
Back to the
Yeah.
original image.
Yeah.
So
more like clip, right? It's more like clip.
The cost.
Okay, I think it almost have no cost. Now, what is the question and what is the confusion?
I think we have already
clarified
the confusion.
Okay. Maybe I think everyone is cleared on this point.
So, because this encoding function seems like it is non-differentiable, but actually the paper can represent it in a differentiable way. So yeah, it's like a clipping function. So the X is the input, so X is the image. The X here is just the A in the previous slide. And the output is tau. The tau is just the B in this slide. And let X to be the input, tau to be the output. The length of tau is L, which is basically 10 here. And the case entry of tau is just to take X minus K divided by L, then clip it to be between 0 and 1. Then we take the floor function. Yeah.
And can you mention what's the shape of the tau?
Tau has the same shape as B. So it's a vector of length 10.
For example, given the X, after we do the encoding, so let's say EX.
Yeah.
So EX is more like the step function. This is E, and this is X. So we have something like this, right? And then the maximum number is 1.0, and this is 0.1, right?
But we don't sum up, so we will not have this stepwise function. We will just have the encoding. We will not sum up. Yeah,
I understand. So this is encoding vectors.
Just an encoding vector.
So let's assume that. Okay, so suppose the value x values here is more like 0, 1, 1, 1, 1, right? And this is here is like 0, 0, 1, 1. Okay, so it seems there's a no share here. Okay, we'll go back to slides. So max xij is vector.
Is the value A?
It's
the real value A?
Okay, so the real value A.
So can you give an example here? So it's quite confusing.
Okay, so if x is 0.13, then suppose now my k is equal to 1, then 0.13 minus 1 over 10 is 0.3, right? So the first entry of tau is just 0.3.
0.03 or
0.03, yeah. Then you take the floor function and it becomes 0, right? So the first entry is 0. Then for k is equal to 2, the tau 2 is equal to 0.13 minus 0.2. And because it's less than 0,
so it's still 0. So it's still 0.
Sorry.
What is tau with a head and tau without a head?
It's after apply floor function. The
So
tau is the result of floor function apply tau hat.
Okay.
But I didn't see the continuous, how the continuous can work. How does apply makes the discrete value continuous?
Yeah.
I'm gonna get a little bit confused here. So the point that we're going to translate the vectors into a scalar value or continuous scalar value.
No, they want this tau to have the same effect as the original.
Oh.
Yeah.
Oh.
Okay, but the tau itself is continuous.
Yeah, the tau itself can be differentiated. So.
So let me see. The original value of 0.13, the encoding of 0.13 is 0.
0, 1, 1, 1, 1. Yeah. And
let me can I check this one? Check this one again. Okay, if k is 9, okay, it's 0 or 1. So let me look at this one. So the first one is 0.1, 0.3. So it is. Somehow, do you have a miscalculation here? So if x is equal to 0.13, and the first will definitely be 0, right? And it will be And the next one, and so maximum. So it's supposed to be a value larger than 1, right? So is there a missing absolute value here? So,
Oh, this is the original screenshot that I took from the paper.
okay. So it's just it is minus. So suppose in the extreme case, it's supposed to be 1, right?
0.
The extreme number is 0.9, right?
Yeah.
Or the k is 9 or 10. Suppose it's 10, these will be negative values, and all the rest will be 0. Right. So, but the point is that either this component will be a value greater than 1, or this should be a max. Yeah, I'm not sure if this is max. No. 0. Yeah, but anyway, let's forget about this formula. We always can find such a formula which makes either choosing a max and the minimum between 0 and 1, right? So the point is that either this is supposed to be a 0 or supposed to be a value greater than 1.
Yeah.
Right? Then we can play the tricks. Anyway, there's a way to do this. Maybe you can, let's forget about the formulas. Even if the formula is incorrect, we can always come up with a way to do the trick. So keep going on. What if such a trick work, and what can we infer from that?
So I will put all the results at the end after I introduce all the 3 research questions. The second research question.
No, we haven't answered questions.
Yeah.
We haven't answered the question. What if the trick works? So we replace this one, and the gradient descent can.
Yeah, it can work.
It can work. Okay.
Can work. I will introduce at the end. So here I have a table.
Okay.
The second research question is that is it effective to attack stochastic gradients with expectation over transformation?
Wait, I still have a question last slide. So the floor function differentiable. Remember, we apply step rule. And the step rule functions, we just using a floor function to enhance the step rule, right? We do not have a lot of if else there. And then we find that FGSM simply does not work.
Yeah, I think this part is really strange because if I use the floor function in PyTorch, then the gradient will become 0. But here, they claim that using floor function is still a differentiable. Eh? Oh. Wait. They use tau prime x instead of tau x. Right. So here they said they use tau prime x as the jx, not tau x.
So it actually changed the gradient here.
Yeah.
So here is a little bit tricky. So I think I have a research I sense a research opportunity here. But the point is that we somehow using a continuous function to replace the non-continuous or discrete functions. But whether we can generalize it. For example, they just proposed an approach to replace this flaw, right? So basically.
Oh, no. I think just forget about this line because here they said they used the tau prime x.
I understand the original encodings is just apply a flaw there. It's just to apply a flaw there. Right. So if we apply a flaw, it is just an encoding here. So here the trick part is that there's a lot of if-else approach, and they come up with a way using a formula to represent those if-else shape. then you find that the only difference of this way is that you apply a floor here. So you're just using a floor, you remove the floors and everything becomes continuous. And I assume here is that so I do feel this kind of way. If you do, if you can apply the floor functions, it is somehow it is supposed to be. Hey, this floor is not ceiling, right? It is floor. If it is floor, it should always be 0, right? So if you want to be 1, it has to be 1.2, something like this. Then after your floor, if we apply floor here, it will be 1, right? That means the outcome of the minimum will be 1.2. However, if you're using 1.2 and the minimum value is 1, so somehow I just do.
If it is 1, then taking the floor, it is still 1. So I think here.
So to make sure that
it can still have 1, yeah.
So we need to make sure. So this make sure this one should always be greater than, but sometimes should be greater than 1, right? This value should be greater than 1, and getting this value is always below, is in between 0 and 1, and unless this is negative values, otherwise it will not be 1.
Yeah.
Okay, I just come back about this formula. Let's forget about formulas. So my point is here. Anyway,
what if we replace the 1 with 0.1? The last
0.1.
Yeah, 0.1, and then we times the whole formulation by 10.
By 10.
Yeah.
So in this case, your point, please go on.
So, in this case.
So the point is, let's say the k equals 9. The k equals 9, and this one minus 0.9. It's a negative number, it will be 0, and it will still be 0.
Okay.
So whatever it is. So maybe there's a problem of this formula. But my point is that whether we have a generalized way to detect all the different techniques, and we do not need to play this trick. So this trick can work because we know exactly how the encoding is. So I'm talking about a broad picture. So suppose we can design maybe the step function like this, right? If possible. But if we design the step function like this, or we design some jumper loop like this, right? So there's many ways to defend the guidance. But if we want to get it smooth, we somehow need a way to, like a regression function, to somehow need to do the estimation here. And the trick to change from discrete values into continuous value is that we need to smoothing. The idea that we smoothing the gradients, then we replace the original function with what we have smooth. So in this case, I feel that there's a research opportunity here. So I think the gradient masking. So the only way to overcome the gradient masking is that we need to find a way to smooth. But they have many ways to apply the gradient masking. So somehow, if we would like to have a research work like that, we somehow need to collect a lot of the, maybe we can construct a lot of the discrete functions or gradient masking functions, or to try to insert all existing gradient masking technique for a given method to let it be defensive to deal with the adversarial attacks. Then we propose another smoothing technique. In this approach, they just propose one smoothing technique for one particular gradient masking. So I'm asking the question whether there is a universal or there is a general way to detect any existing gradient masking approach. Second, if we detected whether there is a universal or general approach to automatically smoothing them and to continue the adversarial attack. So I'm asking these two questions. So maybe this could be your another research work in PhD. Yeah. Okay, keep going on. Good that we have something interesting to discuss, and hopefully there's no existing research work on that because we still need to work on the PDB paper for the time being.
So the second research question is that is it effective to attack stochastic gradient with expectation over transformation? So to answer this question, it attacks the defense technique I introduced, the stochastic activation pruning. So for stochastic activation pruning, during test time, it randomly drops some neurons with probability inversely proportional to their absolute value, which means the lower the activation value is, the higher the dropout rate. So they think if the activation value is high, then this neuron is relatively more important. And it is unlike, yeah. Okay, so to attack, we are going to take the average gradient instead of a single estimation of gradient, and then use this estimate to attack.
Okay, that's very easy to understand.
Okay, so the last research question is it effective to attack vanishing or exploding gradients with reparameterization? The paper selects defense scan as the attacking model. First, I will introduce how defense scan works. Step 1 of defense scan is to train a classifier in normal way. And step 2 is we train a GAN on clean images and only keep the generator part for later steps. So you can imagine generator as a decoder. The input for generator is a vector, and the output is an image that looks like training images. Since the training data are clean images, then a well-trained generator has the ability to project the vector onto clean data manifold. Okay.
Okay, so is there any questions on this side? Sunny, do you have a question here?
No.
No, okay, please go on.
Step 3 is now we have a pre-trained generator and a pre-trained classifier. Now, given a testing image X, I'm first going to find a vector Z that best represents X. So this Z is found through this optimization network. And then we feed this vector into the generator. Because we know if the generator is well trained, it can project my Z onto the clean manifold. So somehow my testing image X gets purified, becomes X prime. Then we feed this purified image X prime into the pre-trained classifier.
Here is stuff. So for these model structures, of course, we choose the GANs and it will always generate an image, always generate images conforming to distribution or training data set. But what if it is fitting to an input images, which is the blank image or the pure black images, and in that case, we'll always generate images. For example, we using a saber 10 images. So given the arbitrary images feeding the network, will these structures always generate an animal images for it and do the prediction?
In theory, it should generate an image that falls under the same distribution as my training data.
So I think maybe I'm a little off topic of the virtual defense. But as for the model architecture here, I think this architecture will lose the component of how how far away these images is from the generator. Or maybe we're using a discriminator here. So we first use discriminator to evaluate whether these images is somehow close to our training data. So if there's an arbitrary images here, it will always make a prediction. So, but that's not necessarily the case. Sometimes it will just give me a random noise here. Then definitely this is optimized function. As long as I find a global optimer, the star will begin to generate images. So the first step is that we need a judger, or we need a classifier or something else, maybe discriminator with the job, to verify whether this image is worthwhile for us to do prediction, or that's more like a defender of the defender. We first using a filter to throw away some ridiculous images or some arbitrary noise, etc. And after filtering for that, we feed the images into the optimizer to let them do optimization.
But if you have a discriminator, then why do you need to do if you have a discriminator that can tell whether this is a clean or adversarial, then
No. The discriminator is going to say whether it's worthwhile to take the images into the generator, or whether it is worthwhile to using the generator for a specific Z to generate new images. So the example is that given images is a pure blank or pure white image or full of noise. So in this case, by this architecture, it will always find a Z star. This Z star may represent a cat or a pig or a horse, whatever, to represent, because this horse or this cat is the most similar images to this red noise. So the will use the classifier to say this red noise is actually a horse or a cat, right? But before that, my suggestion is that for this architecture, of course, it is invented for the goal of defending the adversaries. But in practice, we might still need another defender or filter to get rid of the irrelevant images, then apply this architecture. That will be more seems more reasonable. Yeah. So that's here is just a comment here. Okay, next one. And Shani, I assume that you can follow here, right? Shani.
Somehow the overall idea.
Okay.
So once again, there are in total 3 steps for defense scan. The first step is to train a classifier. Step 2 is to train a generator. And step 3 is to connect the optimization network, which can convert X to a hidden vector Z. Then we feed Z into the pre-trained generator and pre-trained classifier.
So here, one comment is that we may not need to train the classifier because it is talking about the defense technique. So this classifier is what we take off the shelf. It is all off the shelf classifier. Or that is classifier we need to protect it. So it is something we take from the others.
Okay, so defense scan can create vanishing or exploding gradients because this optimization.
Sorry, but here I have one more question. So why here we only have a limited number of Z?
These are like the seeds, the random seed for Z. Here we're trying to find a Z that can represent X. So yeah.
Oh, okay.
Okay. Defense scan is deep because this optimization loops is really deep. So yeah. And how do we attack is that we do a reparameterization. So recall that I have mentioned this Z adversarial. So this Z adversarial is just the Z star here. suppose we only need to find Z adversarial instead of X adversarial. Then the backpropagation path of Z stops before the optimization loop. So it is easier to find Z.
Getting the decoder or the G itself is differentiable. We can just generate an image at X prime, right?
So recall that in reparameterization, so there is a relationship between X adversarial and Z adversarial. So this relationship is just the generator here. And the small g is the optimization loops plus the generator part, and F is the classifier part. In defense scan, my X adversarial is just capital J of Z adversarial. And because the J adversarial is already on the clean manifold, so if we fit the JZ into the optimization loop plus the generator, because these two things will just project the vector onto the clean manifold because it is already on it. So if you fit it into these two networks again, you should expect that the output is just equal to the input. So J of HZ adversarial is equal to HZ adversarial.
Okay. Any question here? I think it's somehow clear here.
Then we only need to find Z adversarial instead of X adversarial. And after we find Z adversarial, because we know there's a relationship between X and Z, we just let X adversarial equal to JZ. Yeah.
Okay.
So these are the answers for 3 research questions. For the first 2, they find the attack is very successful. But for the last question, they failed to attack the defense scan. But they argue that the fault is not that their reparameterization is not efficient. They argue that it's because the generator is not well trained, so it cannot completely project samples onto clean manifold. Yeah.
So there's always a cost. So just go back to the architecture. So I just feel that this architecture, it is very elegant in terms of the idea, in the idea levels. But in practice, it always, because there is always a trick here. So for generators, there's a very famous dilemma for training the generator when Yang Hong is here. So one of the observations is that suppose when Yang Hong was here, he using generator to generate the face, the human face, but sometimes it will have the ridiculous result, like it will generate the mustard for the woman's, or it will make the woman look like a man or something like that. So, but one of the dilemma for training the generator is that when the generator will generate the local optimum. So do you still remember for GANs, they're the generators and they're the discriminators, right? And Xiaoying, do you know about, okay, Xiaoying is going to leave go.
Yeah, I need to go now.
Okay. You should have the appointment, right? The appointment is ready.
Yeah.
Okay.
It's really the last minute. But
Okay.
what's your question again? I can...
So no worry. So let me finish explaining. For the generators, here are the generator discriminators. So usually the discriminator is much stronger than the generator. So in general, when we train the generators, the goal is that we're going to generate a picture, makes the discriminator believe it is true, right? So in general, in the training set, we have cat, dog, pig, except for horse, etc. So suppose the generator did a very good job on cat, but it did not a good job in the other category. So in this case, the generator will always keep generating cat. So whatever Z it is, it always generates a cat. So in this case, the generator will have a local optima of keeping generating one images or one category, or in the worst case, the generator always keep generating only one image or one samples. So that's a dilemma. So I don't know how the authors or the researchers are proposing these ones and how they avoid the generators. But once we include the generator, there always such a dilemma. And this dilemma maybe Xiangling will encounter such a dilemma when you're using autoencoder. Might be. So when doing this, we need to pay this attention. Okay, so that's my comments.
So I only introduced 3 of the works. Actually, they have done in total 7 experiments, but I just select 3 of them because the rest are similar. Okay, so this 8 defense work are all from ICLR in the same year. Okay, and
Okay.
they find that nearly all of the defense are not working after attack. Defense.
All the attacks, all the defense. Oh, sorry.
Yeah.
So
yeah, these are all the defenses. Yeah. And this is the accuracy after attack.
it's the defense technique. Oh, okay. So it's defense. It's the defense is not working anymore, right? Okay, the defense. Yeah.
They are trying to attack these defense methods.
So they tried all of them. They tried all of them.
Yeah, they try all of them.
And resistance are for. Let's see. So the last one is about the transformation-based approach, right? Am I correct?
The last transformation.
So 3 categories. So the gradient. So 3 categories: the gradient maskings, the stochastic gradients, and the third is the input transformation.
All the 3 types are called gradient masking. The first type is actually called shattered gradient. That means non-differentiable network. So the first 3 are from the first type. And then these 2 are from the random gradient, stochastic gradient type. Then these 2 are from the really deep network type.
It's called deep, but it
sounds
to me.
vanishing gradient.
It sounds to me that I feel that the input transformation cannot fall into the category of the gradient obfuscation or gradient masking because input transformation is just like totally changing the original input into another one.
This paper I have presented before. So in total, they propose 5 methods.
Like I understand. I remember that. But I'm saying that the input transformation cannot fall into the gradient masking approach because the gradient is not there. So the input is totally changing into another picture.
No. But the thermometer encoding is just input transformation, right? You just transform the input before feeding into the classifier.
From the field, but okay, you believe this is input transformation?
Yeah.
It is. It's more like discretizing the image value.
Yeah, but you can imagine it as a transformation.
That's how do we define what a transformation is.
Yeah.
So here, I just feel, at least for the last defense scan, or maybe the pixel defense. I think you didn't introduce what a pixel defense is, but I assume that this approach will, for example, for the defense scan, it uses a transformer to totally transform it into another picture, and then also there's the chances that giving a black images or the random noises, and this again will change into a cat or dog, right? So this kind of images, I think, is more like transformation, the random transformation.
Hmm.
Sorry, the input transformation. And for this input transformation, it's actually not relevant to the gradient anymore. Because all the image is we're totally using a new image, and there's no clue from the y. There's almost no clue from the y hat to yx, right? So the original adversary is going to calculate the gradient of y, the partial derivative of y over x, right? But now we have a completely new x prime.
Yeah, but the attacker knows that you are using this defense strategy, so
Yes.
Yeah.
Yeah.
So the transformation on input, the attacker will add it into their model.
I understand there's way. So here, I think we should, I think those categories are fine, but they somehow using. So for these, for the first category, there's somehow a clue. There's somehow a clue between. Somehow there's a clue using the original image, right? So, but for the latter one, or for the third categories, there's very hard to using the original X as a reference to continuous attack. Okay, please go on. Please go on. So actually, this is approach to systematically evaluate all the defense techniques. Okay, keep going on.
So the author gives some suggestions for those adversarial defense works. The first one is towards the definition of threat model. This suggests the researchers should specify every detail of the threat model. For example, whether the attacker can have access to model architecture with training algorithm, training data, test time, randomness, and query access. And also, the author suggests that the researcher should make realistic assumption for threat model. The attacker should at least have knowledge of model architecture, training algorithm, and can allow query access. And also, we should not restrict the attacker's computational power because the attacker can spend as many iterations to attack. And second suggestion is towards the ease of replicating the experiment. First one is that the researchers should make clear claims in their papers. For example, this is an example of clear claims. Specify the final accuracy and what is the distortion type and what is the perturbation strength and what is the threat model condition. And also need to specify all the hyperparameters in the defense model. And also, for the defense papers, we need to consider adaptive attack scenario. That is when the attacker has knowledge of what defense strategy is being used.
Let me see the last slide. So, okay, so you have finished the presentation now, right? Yeah, so this is, I'm going to say this is a very clear and perfect presentation. And as mentioned here, one of the interesting topics here is yes, the offsets at one point there's vulnerabilities and there's also something we can do even if we adopt the gradient masking approach. The gradient masking approach we're talking about is that we're using some encodings. So how do you call the first category? It is called gradient masking.
Shattered gradient.
The shattered gradient. So basically, the idea that let's call it the gradient disappearing approach. How about you? So for the first, so from my point of view, my first observation is that for the stochastic approach, definitely so there's always a trade-off between the original model accuracy and the defense technique. If you want the model to be defensive to the adversary attack, you somehow need to change the performance or the behavior of the model. The more you change the behavior, the more likely the performance of the model will be affected, right? So in this case, I think one of the worst, but just from my point, maybe it's not correct. I think the worst or the most dangerous way is that we adopt the stochastic approach. That makes the model behavior unpredictable. So since we introduced the non-determinisms, the model behavior becomes even harder to predict. In this case, the people will never know. Suppose this model is used in, for example, autonomous driving, when used in surgery, for example. If you're using the random dropouts on the original models, I'm really curious about how many patients is now that these machines or this model performing my surgery. You can please. We are still recording. Maybe you can still sharing the profile. You can still sharing the screen. So how many? So I just wondering how many. I'm just wondering how many patients are willing to let a model with non-deterministic decisions to operate on themselves, right? So this is the first from the practical perspective. I think the second one that is a random approach might be choice. I think that I do have a concern for the second one. As for the third ones, the idea, as I have said, the idea is perfect. So we using the GAN to transform the images, but maybe it's about the limited of my expertise. I also have concern on these GAN-based transformation approach. So when we do the transformations, it also influences the model behavior a lot because we are not using the original images. We're using the GAN to generate it. And when we include GAN, we somehow need a more robust GAN or more reliable GAN to generate the pictures. And given the pictures are completely generated from scratch. So somehow I do have a concern for its practical value for that. So here, one of the things, if I'm the one for current stage, is going to defend attack, I somehow is going to using the gradient disappearing approach. That is first category. For the first categories, as long as I discretize the continuous functions, and the model accuracy is almost preserved, and the gradient disappears. And as for, and we can have a lot of architecture doing this. So maybe now it's time to annotate it here. So given the first category, so I have already make an argument that the third and the second maybe have the problems. Maybe I leave it here because we're recording, so I leave note here. The second category, because the randomness will introduce the non-deterministic, and the non-deterministic actually raise the concern of its practical use, especially for the life critical values, especially for when you're using model to trading, we're using model of autonomous driving, we're using model for surgery, and the non-deterministic decision is the last thing we want. So here is the problem. Here are the problems. Here are the problems of the practical. So we believe that somehow it's not that practical. And the first third, the performance of the original model, because when we're talking about the adversary sample defense technique, we always trade between the model accuracy and its robustness, right? So if the model is not accurate anymore, it makes no sense. It makes no sense for it to defend the adversary. So in this case, the third approach is heavily reliant on the performance of GAN. the GANs, if the GAN reliable, how reliable the GANs, and whether the GAN can always transform the original images into the I prime, into I prime. So for this part, I still have a very large question to doing this. And if we introduce one more GAN, and the performance and what is called on the accuracy of our new models, I still have the question. Of course, this is a very interesting area for us to explore. If we have enough manpower, it is very interesting for us to explore. But the first one, I'm going to say this safe. The gradient disappearing approach, I mean, it's very safe because we just change a minor function and the model performance is almost preserved. The only problem is that the people is very easy for us to estimate, right? It's good estimation. As long as we can have a good estimation of this discretized gradient, then the attacker can resume the adversarial attack. So one possible way is that, so anyway, so we have two perspectives to think about this problem. So the first is that from the attack for the black hat perspective, the other is from the white box, the white hat perspective. For the black hat perspective, that is two questions. There are two questions that we are asked in the middle of discussion. The first is that for these papers, it only attack one gradient masking or the gradient disappearing approach, right? But given this philosophy,
it attacks three actually.
Okay, three. That's fine. One is three. And then giving three. But giving this style of discretizing the approach, and we can have a lot of way to design or discretizing the model behavior, right? As long as we discretize it in some part of the approach, and the model gradients just disappear, and whether there is a universal or general way to identify all the parts of the gradient, all the parts of the gradient masking, on all the parts of discretization, right? So universal is called the discretization detection. The second is that smoothing. So giving an arbitrary discretizations, whether there is an arbitrary smoothing technique to go. So there's two questions, and if we can solve these two questions, I assume that we have another good submission. We're going to have a good submission for that. The second is for the white box, because once we adopt this gradient masking or gradient disappearing approach, so we cannot avoid the model as long as the model is weak. We cannot avoid attacker to detect them. So suppose there's already a technique to automatically detect those discretizations and the model is gone. As long as the discretization there, we can always, I think my gut feeling that we can always find a way to smoothing them. So one very useful way is that from the architecture point of view, we can design the architecture in two parts. One part of the model, a part of the model is available to the model, available to the attackers, but another part of the model, so that's a model which using discretization, we leave it in the another part, which is called SGX. SGX is, so that means we divide the model in two parts. One part is available to everyone, is visible to everyone. Another part, we need to encrypt it with some technique. We need to encrypt it with some technique. So attacker cannot see or cannot, or let's say this part of information is not visible to anyone. It only be visible when in the runtime, and the runtime environment is in some encrypted environment. So in this case, the attacker can never do the tracking. So this is about another security settings. So two parts. The first part is that I think this paper actually point out promising the direction without universal or general discretization detections and universal discretization, smoothing. So as long as we address these two issues, there will be another papers. And secondly, is for the deployment. If we know there's approach and smoothing all the discretization, and what can we do to further protect the information? Yeah, so I think there's two interesting part here for us to further to investigate. Okay, that's all my comments. I think these discussions take a longer time than I expected, and also there's a lot of information for us to digest. And thanks Ruofan for his great presentations, and thanks for a lot of people, Qingzhou and Yihao, who is still attending here. Is there anyone have other questions? Okay, if there's no other questions, let's call it a day. And thanks again for Ruofan.
Thank you. Bye-bye.
Bye.
Thank you.